1, or why do we factorize in terms of 3 terms instead of just 2? What happens is that in solving an integral equation, you want to calculate the scattering with different groups of sources. Say you have a group of sources that you have over here, that you have discretized into subdomains, and you want to study the interaction of those group of sources with this other group over here. So there are 2 groups over here. And this factorization allows you an alternative way of studying this interaction. First, the direct translation will be going from I to j, right? You might have rows of I located here, and then rows of j located here. And this would be directly going from I to j, right? That would be going directly from I to j. This factorization allows you not to do this directly. You can first collect all the sources in this group to an origin called L, okay, which I call OL, but let's just call it L. Okay, you start with I, OI, and then you translate to L. Collect all the sources to the origin L. So all the sources within this group can be collected in this manner. And then you can translate from this box center to that box center, or group center to that group center, L prime. Okay. And then after you have done the first translation, this first translation is a Hankel to Hankel translation. This is Hankel to Hankel. It changes a Hankel wave, a monopole emanating from this point, to a Hankel wave emanating from that point. This is what the translation does the first time around. The second translation changes this Hankel wave into a standing wave about this region. Okay, it's actually valid over a pretty large circle. Okay, but it changes into a Basel wave is what it does in the second translation. And then the last translation changes this Basel wave to be a Basel wave evaluated at rho j. That's what the last translation does. That's why we have this pre-factorization. So instead of a direct interaction between all the group members, we can first aggregate all the field to one group center, translate it from group center to group center, and disaggregate. This usually I call aggregation. This I call disaggregation. This I call the translation. Okay. So this is the general physics of the thing. But this could still be quite costly because the center matrix is dense. Okay, this is a dense matrix system. So this could be P by 1, this could be P by P, this could be 1 by P. So this translation from here to here, the alpha translation involves P by P. Okay, it's a dense translation, it can be expensive. And if we divide this into different group centers, okay, there could be a lot of center to center translation. So if you can diagonalize this factorization, the center to center translation will be a lot cheaper. So the next thing we need to do is to find a diagonal representation of this. So the center to center, group center to group center translations become a lot cheaper. And overall, it becomes a faster algorithm. So next thing I'd like to talk about is diagonalization. How do I make the center part diagonal? Okay. For the 2D cases, actually, you can take a lot of shortcuts to obtain a diagonal representation. Okay, one way to notice is that this alpha translation and the beta translations are just convolutions, actually in 2 dimensions. Okay. And if I were to write this thing out explicitly, it will look something like this. It will have The beta is a Bessel function, remember? The beta are the Bessel function. The alpha is the Hankel function. If I were to write this out explicitly, then I have a multiplying by a Bessel function vector. Okay. And if I turn out that if I worked out everything correctly, this is how it looks like. Okay. And then the center translation is the Hankel function. If I write out the matrix vector product correctly, it will look something like this, involving Hankel functions. And then with the correct matrix element, which you can glean off from the translational addition theorem. Okay? And then the last one is this matrix multiplied by that vector, and you can write down the vector as such. Jn k rho Li e to the minus n phi Li. Okay, if I write it out explicitly, this will be how that looks like. It turns out that rho Li is this distance over here. Rho Li, and then this one. Okay. And then it turns out that this series always converges. Okay, this series always converges because of what? Because rho Li is less than rho L prime rho. If you look at this picture, rho Li is this distance over here. Rho L prime is across the two centers of the group. And you notice that this thing over here goes as 1 over k rho L prime L to the power of n minus m. Okay, when n minus m tends to infinity, when the order of the Hankel function tends to infinity, the Hankel function behaves like that. But the Bessel function has a property that it becomes k rho Li to the n when n tends to infinity. Okay, it behaves like that. So when n tends to infinity, this term always goes to 0 faster than this term would grow. When n tends to infinity, I can say when n tends to infinity, okay? That term grows to 0 much faster than that term goes to infinity. So that center thing always converges because of the relationship between these two, because I have made sure that the addition theorem is not violated. That convergence is very good. So because of that, I can actually replace this with a finite term. I will replace that with a finite term that is n minus p to n plus p. Okay? I replace it centered about the center of this thing here. Okay? And if you look at the inner thing, it's just a discrete convolution. It's a discrete convolution. It's a discrete convolution, n minus m, so it's a discrete convolution. Because it's a discrete convolution, generally it takes n squared to do a convolution. But if you go to the Fourier space, it takes order n. You just multiply two column vectors together. Okay? It becomes order n. In other words, if you have a discrete convolution, the matrix only depends on the n minus m. So all these elements are the same. And if you multiply this with a column vector, this cost is generally n squared cost. It costs you m squared. If this is m by m, it costs you m squared to do this discrete convolution naively. But if you take this to the Fourier space, take this to the Fourier space, this thing becomes a scalar column. This thing becomes a scalar column. So you just multiply the two together. It costs you order m instead of order m squared. Okay. And then you can obtain the result of this by Fourier transform. Bring this to the Fourier space, Fourier transform into the Fourier space. And then you have to multiply this with another vector here. So after you have done the discrete convolution there, you will have something like this to perform. Jm e to the im multiplied by the result of that, let me call it alpha m. The result of this will give you alpha m, right? And this alpha m can be obtained in the Fourier space very easily. But this is an inner product in the coordinate space. But something that is an inner product in the coordinate space is also an inner product in the Fourier space. So the best thing is to take this to the Fourier space also, so that this becomes an inner product in the Fourier space as well. So when I do the first convolution, I will leave everything in the Fourier space. Take this to the Fourier space and do this inner product. Okay, can you follow that? So this is a convolution. I take this convolution to the Fourier space. The leftover thing is this Passavant's theorem. Passavant's theorem is an inner product. Remember, Passavant's theorem says that inner product is independent of what space you do it in. I must well do this inner product in the Fourier space. So I can actually arrive at a diagonalized form of this translation operator by taking things to the Fourier space. So what I have is that this thing, H01, K rho Ji, can be written as this inner product in the Fourier space. Okay? Which in the Fourier space, if you have a discrete Fourier series, the Fourier space is an integration over alpha from 0 to 2 pi. Okay, for discrete convolution. And then I look at what this is in the Fourier space. It turns out that this is a closed form Fourier transform. This term. And I will call that beta. This is the equivalent of JL. Okay. I will call it beta JL. JL prime alpha. It has an exact Fourier transform in closed form. I'll give you the expression later on. Okay, it has an exact Fourier transform. The second term is a matrix. It does not have an exact Fourier transform, but I can find it numerically. I call it alpha L prime L. So this is this thing. I can take this matrix system and take it to the Fourier space. It just becomes a scalar number. Okay? And then the last term over here can also be found in the Fourier space in closed form. So the whole thing finally can be written in this manner by using discrete Fourier transform, by noticing the fact that the first operation is a convolution. The convolution can be written as a product in the Fourier space. So after I have obtained the product, I leave the result in the Fourier space. Take this to the Fourier space, perform the inner product by using Passavant's theorem. And this is actually convolution followed by Passavant's theorem. I replicate this exactly. Okay? Does this make sense? And is this possible to follow?
Is it very cheap to go to convert that AL L prime L into a Fourier?
Okay, let me tell you, these two terms have closed forms.
Yeah.
The middle term does not. Okay, let me tell you what they are. To obtain the closed form for this, you use this identity, the fact that this thing, JL prime, e to the IM, phi L or phi j L prime, okay, has a Fourier identity given by this expression over here, I k rho j L prime cosine of L minus phi j L prime plus I m alpha minus pi over 2, right? This is like the formula that we derived for Bessel function of 0th order. But in the textbook, I show you how you derive this higher order form by using the racing operator. This is also in Whittaker and Watson that we derived in that book as well. But this is an exact identity. The one that we had learned in class is this identity. Something like that. 0 to 2 pi d alpha e to the I k dot rho. The Bessel function of 0th order is essentially this. We apply the racing operator to that, you get this. And this is essentially just e to the I k dot rho. Okay. But you look at this identity, what it does say is that this thing is a discrete Fourier transform of this thing. Because to find a discrete Fourier transform of something, you multiply by you do this and you can find the discrete Fourier transform of this, right? So discrete Fourier transform of this is that, discrete Fourier transform of this is that. Okay? Fourier series transform. Maybe I shouldn't call it discrete Fourier transform, it should be called Fourier series transform. Before Fourier series theorem becomes Fourier transform. Okay. So this has a closed form, which is this thing over here. Similarly, this one also has a closed form. So both of these has a closed form. But this matrix operation in the center has no closed form. In order to compute this Fourier transform, the Fourier transform, this convolutional thing, the alpha tilde L prime L, which is the function of alpha, is just the Fourier transform of this quantity over here, which is given by P equal to minus P to capital P, H of T, 1K rho L prime L e to the minus I P P L prime L minus alpha plus pi over 2. Okay? Essentially, it's just a Fourier transform, this central piece over here. Because this is a convolution of this with that, if I look at this function, what is it? Actually is, and is this term over here, I take this Fourier transform, I get this. I multiply them in Fourier space instead of doing a convolution, and then I do the inner product in Fourier space. Okay? But what does this identity tell you? This identity tells you that originally I have double summations here. If I were to multiply and write this out, I will have a summation that corresponds to this dot product. I will have another summation that corresponds to this dot product. Okay, I have double summation because this thing here is full. I have double summations. But now if I were to implement this on the computer, I can just write this with a single summation. Something like this, delta alpha, beta, maybe it's not a good thing to use I can use Q, okay, beta Q, alpha Q, maybe it's not good to do that, delta alpha, alpha Q delta alpha, beta Q delta alpha. If I look at this thing, I only have one summation. only one summation. It's the same statement as saying that this is diagonalized now. Alpha NM, if it can be replaced with delta NM dm, one of the summations will go away. Right? So this form implies that I have a diagonalized representation of alpha, because there's only one summation involved. There's only one summation involved. No two summations. Okay? And this calculation hence is a lot cheaper than this original calculation. So I can aggregate, translate, disaggregate, but the translation part is a lot cheaper. Okay? Yes?
In your picture, if I had a group of sources that's just adjacent to the place I want to translate to, then I don't think, it's not guaranteed that I always have satisfied the...
Right. These two groups have to be sufficiently far apart so that the use of addition theorem is not violated. These two circles, for instance, cannot overlap with each other. The further apart they are, the better it is. Because the further apart they are, the faster this series will converge. If rho L prime L is much larger than rho Li, then this series converges very fast. Okay? That means that I can truncate this series into a shorter series. And when I do this calculation over here, okay, P can be a smaller number. But if I were to make these two groups very close to each other, then this series converges slowly, which means that I have to make my P larger, and the final calculation over here will involve a larger P. Okay? So, but I have arrived at the diagonalized form of the translator. And I'd like to give you some hindsight. Hindsight as to what we are actually doing here. You can think of this as being a similarity transform, if you wish. You can think of this change of basis, or change from one space to another space, as being a kind of similarity transform. So in this thing, I can think of the beta tilde. I can think of this beta tilde as a common vector. So I can think of beta tilde JL prime as being a similarity transform if I were to multiply it with a thing, I will get back this beta JL prime beta. Okay, I can think of this relationship, the relationship between this in the coordinate space and this in the Fourier space as just kind of a similarity transform. Okay? And I can write this thing over here, or I can write this thing in the new coordinate system as beta JL tilde dot alpha L prime L tilde beta Li tilde. I can think of this new factorization as being written like this, where this is diagonal. Okay, where this is diagonal. And actually, I can think of this diagonalization as coming about because I found this similarity transform. If I found this similarity transform, I found a similar one for this similarity transform. The fact that I can write beta Li multiplied by a matrix S is equal to beta Li vector. If I found this similarity transform for this beta as well as this beta, I plug it in, I have this factorization being equal to this new factorization, Hankel factorization, as being equal to beta tilde dot S dot alpha dot S transpose, I guess I should have a transpose here, times beta. Okay, I can think of this factorization as being transformed to this by similarity transform. the result of the whole thing is that after this similarity transform, this becomes a diagonal matrix. Okay, all the Fourier transform manipulations that I'm doing are just similarity transforms. It's one way to look at them. Okay. So what use does this have? What use does this have? Let's look at how it can be used to speed up fast algorithm, speed up calculations, interactions between sources. Let's assume that we have a group of sources over here, and I want to calculate the interaction between these two groups of sources. And they would be discretized, broken into small pieces by finite element method. Not finite element, usually we call method of moment, but everybody is claiming that everything is finite elements. Okay, so we break them up into small elements and calculate the interactions. And let's assume that there are n pieces over here, and we have n pieces over there. Ordinary naive calculations of the interaction will be n squared, right? N squared. So, but instead I break this into ng groups. Okay. Then each will have m elements. M is usually n over ng. Okay. I do grouping. And then I do the same thing over here. I break this into groups. And there'll be ng group. And then m is equal to n over ng. Okay, I do grouping. So I have grouping, 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 grouping. And each of them has m elements. Okay. If I do a naive calculation using the original method, the aggregation part would be taking the m sources I have in there and producing the aggregation part would be something like this. Essentially, I want to perform this calculation. I want to calculate the interaction of this thing. I want to calculate this interaction, summing up these n sources, and then calculate the interaction over here. I factorize this into three parts. I do the aggregation part. The aggregation part will consist of calculating this. Taking all the I sources from this group and then forming the group central and make as if the wave is coming out from that group central. This is what the first part does. And that cause is that I take m sources, and this is p by 1, but there are m of this to do, so the cost of the first part is p times m. Because I did it for every point source, but the m of them, the cost is p times m, the aggregation part. And then the translation part, going from here to here, I will multiply by this translator. The second part cost is p squared. Okay? And then after I've translated to the box center over here, I can distribute them into n different destination source points. Each of this is 1 by p. I have to repeat this n times again. The last stage of the cost is also p times n. So the total cost is pm plus p squared plus pm. This is the cost. But what is p? And how is p related to m? Okay, how is p related to m? In the discretization procedure, we will take m to be discretized according to how short the wavelength is. Say we expect the current to look something like this, maybe, the current sources to look something like this, and that the current sources have to be varying like a wavelength. Okay, the shorter the wavelength, the faster the current would vary on the scatter. The longer the wavelength, the slower the current would vary. When we usually discretize this into small pieces, we have to make sure that at least Nyquist theorem is true. So if the wavelength is lambda, the discretization at least has to be lambda over 2. That is the most naive case. But it turns out that if we have a current, in addition to the fundamental harmonics, it also has higher order harmonics. So satisfying the Nyquist theorem itself is not enough. So we usually take m to be larger than 2 points per wavelength, maybe 5 points per wavelength, 10 points per wavelength. Okay, so m is roughly proportional to, if I take this size to be d, okay, m is roughly proportional to kd, which is 2 pi times d over lambda. Okay, so if this is, say, this number is 6, right? This number is 6. Then if I use a discretization of 5 points per wavelength, then I would have, if d is about a lambda, okay, then I have m roughly to be 6. If this is 1 lambda, okay, then m is roughly 6. If d is 2 lambda, m will be 12 if I use roughly the discretization of 6 points per wavelength. So m and d are related to each other by Nyquist sampling theorem and so on. So the larger d is, the higher m is. Okay? So p and m are related because of that. How big should I pick p be? How big should p be? Say if I have a group of sources, okay, and it will produce multipoles on the outside. How many multipole moments do I need to represent the field outside correctly? How many multipole moments do I need? It turns out that this follows from antenna array theory, that if this source is large, it produces more multipoles on the outside. If this source is small, it produces a smaller number of multipoles. Is this intuition obvious or not obvious to you? The larger the source is compared to wavelength, the more multipole it produces. Is this agreeable?
It's the same as the spatial Fourier transform.
Spatial Fourier transform, that's true. Okay. The larger this is compared to wavelength, the more multipole it would have. Okay. Let's see how I can argue this more carefully, more precisely. But what it says is that P is also proportional to KD, is what I'm trying to argue. That is, if the group size is large compared to wavelength, I need more multipoles to represent it. If the group size is small, I need a small number of multipoles. Say if the group size M is only a tiny fraction of the wavelength, then I need 1 or 2 terms, because it will only produce the dipole field, or monopole field perhaps. But if the group size is large, it produces higher order multipoles. So P and M are linearly proportional to each other. Okay, is this clear? Let me see. How can I make this clear? Yeah, if you have the intuition that you have in antenna theory, or antenna array theory, that if this array is very large, it produces a lot of side lobes. If this array is very small, it produces no side lobes. Then you can see that P, the number of multipoles, P usually looks something like this because they're multipoles, they're e to the I m phi kind of thing. So if you have a lot of side lobes, you need higher order m's. And hence P is linearly proportional to KB. So this actually is proportional to m squared. This is proportional to m squared. This is proportional to m squared. So there's no gain if you don't diagonalize. There's no gain if you don't diagonalize. If I diagonalize it, so that I have this form, where this central part is a lot cheaper to do. Okay, let's see what I gain. The first part will still be P times M. Okay, the central part, however, becomes P. It drops down to P. The central part becomes, this is still PM. This becomes P. This is PM. The central part becomes just P because it's diagonal. I don't have a dense matrix vector product to perform the second part. I can perform it with a diagonal matrix vector product, which is just order P instead of order P squared. P is the number of multiples that I need, but you also have to remember that these things are now changed to a different beast. This beta tilde actually looks something like this. Beta tilde okay, beta tilde actually looks something like e to the I k dot rho. Like if this is JL prime, this is just JL. Okay. Beta tilde looks something like that because I show you the identity from Whittaker and Watson. The discrete Fourier transform of this is just that. So the first stage, instead of performing with this thing, you perform an operation with this thing. But what is the physical meaning of this? If you perform an operation with this, with the point sources, but now if you do this instead, AI, with a whole bunch of sources,